We start here with a definition of linearly dependent functions, which is a little weird because we are actually more interested in linearly independent functions. But our definition for dependent functions is that a set of functions f1 of x, f2 of x to fn of x is said to be linearly dependent if there exist constants c1 and c2, cn, not all zero, such that c1 f1 of x plus c2 f2 of x all the way up to cn fn of x add up to 0 for every x in the interval. And then by contrast, if the set is not linearly dependent, then we say that it's linearly independent. And again, we're going to be more interested in the second case. So if we consider like f1 of x is equal to e to the x, f2 of x is equal to like x squared plus 3, and then f3 of x is equal to the sine of x. Then the linear combination c1 e to the x plus c2 times x squared plus 3 plus c3 times the sine of x equals 0 for every x only if c1, c2, and c3 are all 0. This is an independent set of functions. By contrast, if we said, say, y1 equals 3e to the 2x and y2 equals 2e to the 2x, this is a dependent set of functions. If I wanted a linear combination, that's what this is, that adds up to 0, all I need to do is multiply 3e to the 2x by negative 2, and then 2e to the 3x by 3. And now what I have is, it's negative 6 and 6, and they add up to 0, right, with the e to the 2x. And what I have is the coefficients c1 and c2 are not all 0, but the linear combination is 0. That's what makes them dependent. You basically can see independence by looking at functions most of the time. However, it's not always obvious, and there is something called a Wronskian. It's a determinant, and the entries of the determinant in the top row are the functions that we're talking about. So if we have functions f1, f2, all the way to fn of x, and they all have n minus 1 derivatives, then we form a determinant with f1, f2, all the way to fn as the top row. The second row is each of their derivatives, and then we go down the line writing down each order of derivative until what we have is a square array of functions, because determinants only exist for square matrices, and we need to have the same number of rows as we have columns. Anyway, this determinant thing of functions is called the Wronskian. And the way it applies to solutions of a differential equation is if we've got functions y1, y2, all the way up to yn that are n solutions of a homogeneous nth order differential equation, then the set of solutions is linearly independent on an interval if and only if the Wronskian of those functions is non-zero for every x in the interval. An important note is that the Wronskian is either always or never 0 on a given interval. Let's see what it looks like to compute a Wronskian here. We have functions f1 of x is equal to the cosine of 2x, f2 of x is equal to 1, and f3 of x is equal to the cosine squared of x. The Wronskian is going to tell us whether these are linearly independent on the interval. W of f1, f2, and f3 is a 3 by 3 determinant where the top row is the cosine of 2x, 1, and the cosine squared of x. The second row is each of those derivatives. So the cosine of 2x has a derivative of negative 2 times the sine of 2x. 1 has a derivative that is 0. And the cosine squared of x, we need to use the power rule. So 2 cosine of x. And the chain rule, so it's actually negative 2 cosine of x times the sine of x. Continuing with our derivatives, back to negative 2 sine of 2x. That derivative is negative 4 cosine of 2x. 1 differentiated to 0, that derivative is still 0. And then rather than using the product rule for negative 2 cosine x sine x, I'm going to note that's negative sine of 2x. Differentiating that is going to give us negative 2 times the cosine of 2x. If you need to refresh yourself on computing determinants, please do so. I'm going to expand down the middle column because of the zeros. There is a sign pattern for determinants, positive, negative, positive. And expanding down the first column means I'm going to write down negative 1 times the determinant that you get when you cross out the row and column containing that 1. And we've now got a 2 by 2 determinant, which is computed by multiplying the upper left by the lower right, and then subtracting the product of the lower left times the upper right. And you can confirm that by doing that, we end up with terms that subtract out. The result is 0. You may have seen this coming. These are not linearly independent. And as a matter of fact, if we took f1 plus f2 minus 2 times f3, we would end up with 0 because we've just generated the double angle formula for the cosine function. I probably should have said earlier, but I'll say it now. This set of videos is just kind of a few things thrown at you, definitions and theorems. I mean, it was in the title of the thing, preliminary theory. So we're not like solving things right now, but we're laying foundation for what we're going to be seeing. And part of that foundation is something called the superposition principle. There's going to be one for non-homogeneous equations later. This one is for homogeneous equations. Rather than reading it to you, I'm going to tell you what it looks like here. I'm just going to give you an example here. y1 equals e to the 3x and y2 equals e to the negative 5x are solutions to y double prime plus 2y prime minus 15y equals 0. You can check it by differentiating y1, differentiating y1 again, plugging it into this equation, and finding that everything zeroes out. It turns out, so is c1 e to the 3x for any c that's a real number. Any c1 that's a real number, excuse me. So just try it out. Let c1 equal like 7. Differentiate it again, plug it in here. You'll find it works. Same thing for y2. The superposition principle actually says, then so is the function y equals c1 e to the 3x plus c2 e to the negative 5x for every c1 and c2 that are real numbers. In other words, linear combinations of solutions to a linear differential equation are also solutions to the differential equation. That is what the superposition principle says. If y1, y2 up to yk are solutions of an nth order differential equation on an interval, then the linear combination c1y1 plus c2y2 all the way to ckyk is also a solution on the interval. I want to point something out here. Part of what I want you to sensitize yourself to is paying attention to subscripts and other variables that are being presented. In this case, we have an nth order differential equation, and the set of functions that we're talking about is y1, y2 up to yk. It's not so important that that's a k. What I'd like you to sensitize yourself to is that k is not the same as that n. I mean, it could be, but there's no assumption that that k is the same as that n. So that's something called the superposition principle. We're going to see that quite a bit. Now let's move on to another definition. Any set y1, y2 up to yn of n linearly independent solutions, and hopefully that emphasis landed, the number of functions that we have is the same as the order of the differential equation, and that's pretty important here. Anyway, any set of n functions that are solutions to the homogeneous nth order differential equation on an interval I is said to be a fundamental set of solutions on the interval. The important parts here is that we have n solutions to an nth order differential equation and that they're linearly independent. I might call that a full complement of solutions, but I also might be making that up. Let me rephrase this from a different perspective. An nth order differential equation is going to have n independent solutions, linearly independent solutions. And that set of solutions is called a fundamental set of solutions. Brief recap, we saw a superposition principle and then the idea of a fundamental set of solutions. We're going to close this one out by presenting a theorem that combines these two concepts. The general solution for a homogeneous equation. If y1 through yn are a fundamental set of solutions of the homogeneous nth order differential equation, we're referencing equation 1, which was the first one at the very beginning of this video where the right-hand side was equal to 0. Then the general solution is y equals c1 y1 of x plus c2 y2 of x plus all the way through cn yn of x. So this form that I wrote down in the previous discussion here of y equals c1 e to the 3x plus c2 e to the negative 5x, that would actually be the general solution to the differential equation y double prime plus 2y prime minus 15y equals 0. We have two solutions to a second order differential equation, so they're a fundamental set of solutions. Clearly they are linearly independent because the exponents don't match. And the linear combination with arbitrary coefficients is what we call the general solution.